So hello everyone, welcome to the channel. So in this video I'm going to show you the landslide detection using Sentinel-1 SAR imagery in Google Earth Engine. So now let's get started. So in this video I'm going to demonstrate the landslide detection and mapping using Sentinel-1 Synthetic Aperture Radar imagery in Google Earth Engine. So the study focuses on identifying the areas affected by landslide through a change detection approach by analyzing the variation in the radar backscattered value between 2 years in 2019 and 2022. So the first step of workflow, we're going to involve defining our region of interest by accessing the administrative boundary data from FAO, and we're going to define our study area. And this geometry is used to center the map view and constrain all the further processing of the study region. So Sentinel-1 SAR imagery, which provides the cloud penetrating all-weather monitoring capability, is assessed from the Copernicus dataset. A custom function is we're going to define to filter the SAR data based on the spatial extent, date range, instrument mode, and polarization. So the interferometric white swath mode and VV polarizations are selected. So the VV is highly sensitive to the rough surface and changes, which are critical indicator of landslide activity. So only VV backscattered band is extracted for the subsequent analysis. And to assess the terrain changes over time, we're going to generate a mean SAR composite for each year. And further, a change detection is performed by subtracting the 2019 backscattered image from the 2020 image to highlight the variation in the rough surface, which may indicate the landslide activity. And the difference in the image is renamed as a change for clarity. And further, the histogram of backscatter change value is then generated to help visualize the distribution of the pixel level difference across the study area. And further, we're going to apply a threshold based on the histogram. We're going to apply a threshold of -2 decibels is applied to identify the significant decrease in the backscattered, which are the characteristics of the vegetation loss and terrain alteration caused by landslide. So the pixel meeting this criteria are extracted into a binary landslide mask. So once the detected landslide zones are further processed to calculate the areal extent. So this is achieved by multiplying the binary mask by the pixel area and summing the value across the study area, producing an estimate of the total landslide affected area in the study region. And the result of this potential landslide zones will be exported to our Google Drive for further analysis. So let me get back to Earth Engine. So to proceed towards our analysis on detecting the landslide zones, so first we have to define our region of interest. So to define our region of interest, so we're going to use this particular dataset called FAO Global Administrative Unit Layer 2015, and the dataset availability is from 2014, and the dataset provider is FAO UN, and this particular dataset can be accessed through this particular code to access this dataset. So the short description about this data is a Global Administrative Unit Layer compiles and decimates the best available information on administrative units for all countries in the world, providing a contribution to the standardization of spatial dataset representing an administrative unit. So this particular administrative maintains a global layer with a unified coding system at country first and second administrative level where the data is available. It provides the layers on country by country basis down to the third, fourth and lower levels. So you can go through the details about this particular data. Let me get back to Earth Engine. So to create a region of interest, first I'm going to define a variable called Almora is equals to earthengine.feature collection and FAO GAUL 2015 level 2. So once you mention this code, we can access this particular global administrative unit layer, and in that we're going to filter a specific district in India, for example Almora. So to select this particular district, I'm going to use this particular function called .filter earthengine.filter equals to admin name. This is admin name, that is ADM2 name, so which represents the admin name, and I'm going to mention as Almora. And we mentioned once you mention the district of your choice here, in the next step we're going to center this particular layer called map by using map.center object Almora. So you're referring to this particular variable, and we're going to specify the suitable zoom level of 9. And the next step we're going to add this study area, so using map.addLayer, and we're going to mention the variable Almora with the default visualization parameter, and we're going to output the layer as study area. So now let us visualize the result here. I'm going to navigate to the run section. I'm going to click run, and now let us visualize the result. So in the layer section, I'm going to turn on the study area. Now let us visualize the study region. So once you defined your region of interest, that is our study region. So we have defined our study region. So in the next step, we're going to create a function to access the Sentinel-1 SAR imagery, and we're going to apply a set of filters, pre-processing to a Sentinel image. So to do that, so first we're going to define a function called get S1 collection, and we're going to mention the start and end. So the start and end, which represents the starting date of our analysis, and end, which represents the end period of our analysis. And next step, I'm going to mention in this function, I'm going to return Earth Engine dot image collection Copernicus S1 GRD. So this is about our Sentinel-1 SAR imagery. So the Sentinel-1 SAR GRD, a C-band synthetic aperture radar, ground range detected log scaling. So the dataset available from 2014 to 2025, and the dataset provider is European Union, ESA, and Copernicus. And using this particular code, you can access the Sentinel-1 SAR imagery. And these are the following set of band that is available in the Sentinel-1 SAR imagery. So starting with HH, HV, and VV and VH band, we have 4 different bands here. So in that, we're going to specifically select this particular band called single copolarization, vertical transmit and vertical receive, and it has a resolution of 10 meters. So we're going to use this vertical polarization band here. So let me get back to Earth Engine. So now we're going to filter it based on our region of interest. For example, I'm going to filter bound based on our study region called Almora. So we're going to define dot filter bound Almora. And in the next step, we're going to filter it based on the time period of our analysis. So based on the time period, I'm going to mention dot filter date, start and end. So later, we're going to mention the start date and end date of our analysis. So now we're going to mention dot filter date, start and end. And in the next step, we're going to filter it based on the suitable instrument mode. That is, we're going to specifically select interferometric white swath mode. So we're going to use this particular instrument mode called IW, that is interferometric white swath. So to select that particular one, I'm going to mention dot filter Earth Engine dot filter dot equals to instrument mode is equals to IW, that is interferometric white swath. And followed by we're going to filter it based on the transmitter receiver polarization. So we're going to select as a VV, that is vertical polarization. So to select that, we're going to mention dot filter Earth Engine dot filter dot list contain transmitter receiver polarization is VV. So we are applying this particular filter is to use the VV polarization. So it filters the Sentinel-1 image collection to include only those images that contains the VV polarization in their metadata field called the transmitter receiver polarization. And the next step, we're going to select the VV band, that is vertical polarization. So we are selecting this particular band called VV, which is the units in decibels, and the resolution is 10 meters. So select that band, we're going to use dot select VV. So in the next step, we're going to define an yearly mean SAR. We're going to create an yearly mean SAR image. So to create an yearly mean SAR image, we're going to create a function called yearly SAR. And inside this function, I'm going to mention the variable called start is equals to Earth Engine dot date from year, month and day. So the year, so basically it's going to convert the input year into an Earth Engine date object representing. So like this. So it's going to convert the 2019 looking like the date to into mentioning the year, month and day. And in the next step, we're going to define another variable called end is equals to start dot advance by 1 year. So this particular code, it's going to mention that it's going to move the start date forward by 1 year, and this gives the end date for filtering the SAR image. For example, we're going to filter 2019 and 2020 image. So in the next step, to create the yearly mean SAR image, we're going to define another variable called the yearly mean is equals to get S1 collection start date and end date dot mean function. So we are applying mean function to get the yearly mean SAR image. And the next step, we're going to return the yearly image and dot set the year. So we're going to return the yearly mean image. And in the next step, we're going to define another variable called years equals to Earth Engine dot list dot sequence. So the 2019 and 2020 image. So from 2019 to 2020. So we're going to define another variable called yearly image is equals to years dot map function, and we're gonna return the yearly SAR image. So basically it's gonna loop through each year in the year list. And next we're gonna define another variable called yearly collection is equals to earth engine dot image collection, referring to our yearly image. So this one referring to this particular variable, yearly image. And in the next step we're gonna select the first and the last year image. So we're gonna define a variable called first year is equals to yearly collection dot filter earth engine dot filter dot equals to year is equals to 2019, and we're gonna mention dot first function to get the first image out of it, and followed by the next variable we're gonna define another variable called last year is equals to yearly collection dot filter earth engine dot filter dot equals to year 2020, and we're gonna mention dot first function and the yearly collection which referring to this particular variable. So in the next step we're going to use the backscattered value to analyze the change detection between the first year and the last year to identify the changes. So to do that we're going to mention a variable called backscatter change is equals to earth engine dot image last year. We're gonna subtract by first year, and last we're gonna rename as change. And the next step we're gonna plot the histogram for the change value, that is the change detection of backscattered value. So to do that, to plot a histogram for the change detection, we're gonna mention print ui.chart.image.histogram backscatter change, referring to this particular variable, and study region is our study region Almora, and the spatial resolution we're gonna mention is 30. So the resolution of this particular image is 10 meters. So in order to reduce the speed of computation to create this histogram, I'm going to mention it as 30 meters. And the next step, we're going to set an options to this chart here, additional options. For example, I'm going to mention the title. So for that, I'm going to mention dot set options, title, the landslide change histogram, and h-axis, the title is going to be backscatter change in decibels, and the v-axis, the title is going to be pixel count. And now let us visualize the result. I'm going to run this code here, and let us visualize the result. So you can able to see from this histogram here, this is the pixel count. This axis represents the pixel count, and this axis represents the backscatter change dB, that is decibels. So I'm going to view this particular graph in detail here. So you can able to see this graph, the value ranges from -2 to +2. So you can able to see that the highest level of value being indicated in this set of values here. So you can able to see. So to detect the values, that is to detect the landslide region, so we have to focus on the set of values here. For example, we're going to apply the condition where the decibels value are lesser than -2. So the if the condition is lesser than -2, we're going to apply a condition where the decibels value are lesser than -2. So based on the value lesser than this particular -2, we're going to identify those areas. We're going to mark those areas as the landslide regions. Based on the literature survey, I have done it. The value less than -2 decibels, we're going to mark those areas as the landslide regions. So I'm going to mention my condition here. The next step. So the landslide mask. So the area with a strong decrease in the backscattered value. So for example, I'm going to mention the variable landslide mask is equals to backscatter change, which represents this particular variable, and I'm going to apply my condition less than -2. So less than -2 decibels. So based on the value, based on this particular condition, we're going to identify those areas. The condition, the value less than -2, we're going to identify those areas as the landslide prone regions. And the next step, I'm going to mask this area. So to do that, I'm going to mention the variable landslide zones is equals to landslide mask dot update mask landslide mask. So it's going to show us only the landslide areas. So in the next step, to update this mask, we're going to mention the variable. So to mask the landslide areas, we're going to mention a variable called landslide only mask equals to landslide zones, referring to this particular variable, and we're going to mention dot update mask landslide zones. And once you did that, it's going to show only the landslide areas. And the next step, we're going to calculate the total area, the sum of total areas of landslide occurred. So to calculate the total landslide in square kilometers, landslide area in square kilometers, we're going to define another variable, that is landslide zones area is equals to landslide only mask dot multiply earth engine dot image dot pixel area function, and we're going to divide it by 1 is to 10 power 6 to convert from a meter square to kilometer square. So to do that, we're going to mention dot divide 1 is to 10 power 6. And the next step, to calculate the landslide area, we're going to mention another variable called total landslide area is equals to the landslide zone area, which represents this particular variable, and we're going to apply a dot reduced region. So the reducer, I'm going to mention this particular statistical function called sum, using the earth engine dot reducer dot sum function. So it's going to calculate some of the total areas where the landslide zones for this study region. So the geometry I'm going to mention is Almora. The spatial resolution I'm going to mention as 100 to increase the speed of computation. I have mentioned the scale as 100, and to receive as in value, I'm going to mention dot value function, and to get the first value out of it, we're going to mention dot get 0. And last, to visualize the areas of total area where the landslide occurred for the study region, I'm going to mention print estimated landslide area in square kilometers, and earth engine dot number to visualize the number, and they're going to mention the total landslide area referring to this particular variable, and to get it as a rounded number, we're going to mention dot round function. So it give the value as a rounded value. Now let us take a look at this. So let me run this code and visualize the result, the total landslide areas in square kilometers for the study region. So in the console section, we have the estimated landslide area in square kilometers, which is around 1 square kilometers of area. So once we calculated the area, in the next step, we're going to set the visualization for the individual layers, starting with the SAR visualization and the change detection visualization and landslide visualization. So first, we're going to define a variable SAR vis equals to, we're going to set the minimum of -25 to a maximum of 0, and color palettes blue, white, and green. And similarly, we're going to define a visualization parameter for the change detection of the SAR image, using the variable change vis equals to minimum, we're going to set -5 to a maximum of +5, and the color palettes, we're going to start with red, white, and blue. So the variable slide, that is landslide visualization, we're going to mention the variable landslide vis equals to palette yellow, which is going to indicate all the landslide zones. And to add this layer, we're going to mention map.add layer first tier dot clip based on our region of interest, that is Almora, and the visualization is SAR vis, representing this particular variable, and we're going to output a SAR VV 2019. And similarly, we're going to add it for 2020 using map.add layer last year dot clip based on our study region with the visualization of this SAR vis, and output the layer name as SAR VV 2020. And similarly, in the next step, to add the layer for the change detection of SAR imagery, we're going to mention map.add layer, the backscattered change dot clip based on our region of interest, and the visualization is change vis, representing this particular variable, and the output the layer name as backscattered change. And the last layer, we're going to add the landslide zones. So we're going to mention map.add layer landslide zones dot clip based on our study region, and visualization, it's going to represent this particular variable slide vis, and output the layer name as potential landslide zones. So now let us take a look at it. I'm going to run this code and visualize the result here. So now let me navigate to the layer section here, and I'm going to turn on this this particular layer called SAR VV. So that is 2019 imagery, SAR imagery, and I'm going to click this option, and I'm going to mention the custom section to be stretched 90%. So here you can able to see the value ranges from -9 to -3. So I'm going to click apply. And this is the 2019 SAR imagery. You can also select a gamma mode for it and click apply to view the image in detail here. And this is 2019 SAR imagery. So I'm going to close this, and similarly I'm going to turn on this 2020 SAR imagery, and I'm going to select the visualization parameter for it. I'm going to click this option here. So here I'm going to select custom to be stretched 90%, and you can able to see the value ranges from -10 to -3, and I'm going to select a gamma to it, and I'm going to click apply. and this is SAR 2020 imagery. Now let us visualize the difference here. I'm gonna turn off and on SAR 2020 imagery. You can able to see the difference here. So now to identify the changes in this imagery, so we're gonna turn on this particular layer called backscatter change, and I'm gonna turn off all other image here. So we're gonna mention navigate this option, and similarly I'm gonna select stretch 90%, and I'm gonna click apply here. So this is the backscatter change value here. I can also select the gamma value to it, and I'm gonna click apply. So a lot of change. So the high level of changes can be observed in the white values here. So to visualize the changes in depth, so we have to apply this particular condition. So based on the histogram, we applied a condition where the value less than -2 decibels. We're going to classify the values if the lesser than -2 decibels. We're going to consider those areas as a landslide prone areas. So let us visualize that results too. Let me turn on the potential landslide zones, and I'm gonna give it a color. I'm gonna give it a red color to it. I'm gonna close this, and let me take a look. We have this few red spots here in the study region. I'm gonna zoom in here. So you can able to see here. So these are the red spots where the potential landslide might have occurred based on our condition if the value lesser than -2 decibels. So the red areas are the areas where the potential landslide have occurred here. So let me turn off this image, and let me turn to a satellite mode here. So these are the areas where a potential landslide might have occurred here. So I can able to see these red spots here. For example, I'm going to zoom in this part of the area, so which have indicated a red area here. And this particular zone which is closer to a road here, and also a river, you can able to see that. So this particular zone is pretty closer to a road as well as a river. And the next step to export this particular the landslide zone to our Google Drive, so we have to mention this option called export.image.drive. So image, you're going to mention this landslide zones and clip it based on our region of interest, that is our study area. And the description, I'm going to mention this particular landslide zones 2019 and 2020. And the region, I'm going to mention the study area name, and the spatial resolution is 10 meters, and the coordinate reference system, and the max pixel value. So now to export this particular the landslide zone to a Google Drive, we have to navigate to the option called task section, and in that we have this Almora landslide zones 2019-2020. So once submitted task, I'm going to click this option called run, and we have the task name as Almora landslide zone 2019-2020, the coordinate reference system, and the spatial resolution, and we're going to export it to Drive, and as a file name as Almora landslide zones, and the file format is GeoTIFF. To export this image to your Drive, we're going to click this option called run. So now it's going to export this image to our Google Drive. So it's going to take some time to export this particular image to our Google Drive. So it's going to take some time to export this image to our Drive here. So in this video, I have shown you the landslide detection using Sentinel-1 SAR imagery in Google Earth Engine. So thanks for watching, and make sure that you subscribe to our channel and give us a like, and the code link will be given in the description section of this video. So thanks for watching.